Okay, thanks. It's a pleasure to be here, especially to this crowd. I feel like I'm a student again in the last 5 or 10 years. And it's largely because we're building machines that are pretty capable. And I want to give you the story on individual trapped ions as qubits. And they're scalable unlike any other physical platform, partly because this is a picture of 25 atomic clocks. Each atom here is a very good qubit, way better than we need it to be. And we like to say that it's a perfect qubit because when we leave it alone, it has no idle errors. The T1 and T2 times are essentially infinite. That doesn't mean there's a free lunch. We have to control the system, of course, and unlike the other physical platforms, all of the challenges in scaling this platform are on the classical controller side. So there's a lot of engineering that will come to bear in this technology. So we're starting pretty small and lower your sights on almost everything I'm going to talk about. But at the end, I'm going to speculate on how we hope to scale, and it's going to involve a healthy dose of engineering. Okay, so these are 171 ytterbium ions, if you care to know. The main point is they're all absolutely identical, and they store qubits inside the hyperfine levels within each atom. Because they're charged, they of course form this crystal. The spacing between the ions is about 5 microns. So this is a crystal less than about a tenth of a millimeter across. I want to tell you a few minutes just how we generate entanglement between the qubits and then building machines. And there's sort of lots of high-level quantum computation going on. And although I was born and trained as an atomic physicist, in the last many years, I'm starting to appreciate the higher levels of the quantum computer or quantum simulation stack. Okay, so as I said, the hyperfine levels of this 171 ion, one nice thing about this ion is that the nucleus is spin 1/2 and it has a single outer electron. So unlike almost any other field in quantum mechanics, when you learn about hydrogen in your class, we actually use it here in the lab. I always tell my students that. So the quantum numbers are exactly that of hydrogen, at least for the lowest lying levels. So the hyperfine splitting here, instead of being about 1 gigahertz in hydrogen, it's 12.6 gigahertz. And this is the atomic clock. I can write a few more numbers if I want. They have no Zeeman shift to lowest order, so they're impervious to external magnetic fields. And if you shield it, you can, there is a small second order shift. It's greatly under control. And like any atomic physics experiment these days, we detect the effective spin in this qubit up and down by collecting state-dependent fluorescence when we shine appropriate laser light. I won't get into too many details, but suffice to say that in a single shot, we can discriminate between up and down with however many nines you really need. The record is, I think, 4.5 nines, but you don't need 4.5 nines if you only have 20 or 100 qubits. So as we build the system up, we know we can pull techniques out to increase this. So for most of the data I'll talk about today, it's about 99% because we're dealing with under 100 spins.
What is it that's 99%?
Oh, the probability that you have measured the state of the ion. Correctly, yes. So incorrectly. Yeah, sorry. So this is a distribution of collected light if you're in the what we call the bright state for obvious reasons, and this is the dark state. So in a single shot, you can clearly see there's great discrimination here. So that 1% is sort of like the overlap.
Can you tell me what a single shot is?
Oh.
I know what a single shot is.
Oh no, this gets interesting. I know we don't have time. I'd love to talk more about this, but this transition is a so-called cycling transition. So the single atom emits 10 million photons per second. We collect a tiny fraction of that. Now, as soon as the first photon's emitted, you can think of the wave function as having collapsed, but we don't know it yet. And so once the wave function, so if you have a 50-50 superposition, you either get all bright or all dark. So it's like tossing a coin and being able to look at it with high fidelity, okay? All right, and most atomic physics systems have this, maybe not to 4 nines, but okay, so I didn't want to dwell on that. But if you're wondering why we picked ytterbium 171, it's actually an engineering reason. And it has to do with the fact that to do all the interesting stuff, the coherent stuff, We don't use microwaves. We could just do NMR, but we want to couple the ions, so we have to apply a force. So we use something akin to optical tweezers. And it turns out something in atomic physics we call the magic wavelength. That's not exactly what this is, but there's an optimum place to tune your laser beam off resonance to do this very efficiently without having start shifts and so forth. And it happens to be a third of the way between the D1 and the D2 lines of the first excited electronic state. And in ytterbium, that magic place is at 355 nanometers. That's an engineering reason because you can buy infinite power at that particular wavelength because it's a very popular laser. This green one is 532. It's the second harmonic of 1064, which is an industrial standard laser that it comes from the neodymium YAG laser. So 355 is used for lithography of CMOS, upper layers of CMOS, and masks. So this laser is incredibly well engineered, and even though I spent a lot of my life inside lasers, this laser has only one adjustment, and it's the on button. And so this is, like I say, we don't think about lasers too much anymore in this system. That's why we picked ytterbium in the end. The downside of ytterbium is it's among the heaviest ions out there, so we have to apply high potentials in the trap to confine the ions. And I haven't talked about that, and I won't talk about that much at all. I want to talk about how we not only flip the spin coherently, but apply entangling gates. So there are several approaches to doing this, and this is a little bit of back-in-the-envelope treatment, but it gives you the essential physics. If we want to entangle any pair of these, and again, they're Coulomb coupled, so their normal modes extend throughout the chain. So right away, we're going to have all-to-all connectivity, as long as you can poke lasers at any of these atoms. We're going to use these two optical tweezers to apply a spin-dependent force. And this is using that 355 laser. I won't go into the details how that arises. It comes from selection rules and so forth. But it's just a dipole force from optical tweezers. But importantly, it can push the ions up or down depending on its qubit. So if the two qubits are up, they both move up together. And their Coulomb interaction, just those two, is exactly what it was. Same with down, down. But down, up, and up, down are a little further apart. And so their Coulomb energy gets modulated. And this is the defect in that energy. You can see it falls like 1 over r cubed. We're effectively making dipoles, electric dipoles, by taking the single charge. If it's in a superposition of spin, we've put the atom in a superposition of position. And that gives us the dipolar interaction that allows us to do gates. So if you look at the 4 possibilities of these 2 qubits, up, up, and down, down remain so, and the other 2 states acquire this phase. Very simple quantum mechanics there. And when that phase is pi over 2, it's equivalent to a controlled NOT gate that can allow you to make Bell states and so forth. Now, this is a hand-waving version that was first spelled out by Serac and Zoller a long time ago, and it was perfected by Mulmer and Sorensen. And this is the kind of gate we use now in all ion trap experiments. There's really no other gate that's risen to the occasion and has the quality of this one. Now, a couple of things I've swept under the rug. The first one is that we don't do it in the z basis of spin. We actually do this spin-dependent force in the x basis. That's a little bit technical. It doesn't really matter. That's the Mulmer-Sorensen technique. And in fact, the native interaction is an Ising interaction. This is also an Ising interaction in the z basis. Okay. The other sleight of hand is that you're probably wondering, what about all the other ions? If you have a bunch of pendulums connected by springs and you wiggle them, they're all going to notice. And that's absolutely true. If you do it really fast, this treatment is just fine. So if we have enough laser power, and that's more researchy, I would say. People don't use those kinds of gates. The gate speeds are typically tens of microseconds or even longer. And the oscillation frequencies are more like a microsecond. So this force acts slowly compared to the vibration. So all the normal modes are coupled. So I won't get into the details, but we can deal with this. It's all classical. We know what all the normal modes are. We calculate them, and we wiggle the pendulums in just the right way. We do laser pulse shaping. We don't just push them. We push them in a very particular, predefined way, depending on the ion pair you want to hit, and we can do a gate and decouple all the modes of motion. What's neat about that is that all the modes of motion are used, so we don't have this 1 over r cubed anymore. It's all to all. And the gates are roughly all the same speed and of the same quality. Now you might ask, well, that won't extend to thousands of qubits. I'll talk about that later, but it will extend to dozens, maybe up to 100. Okay? So right now, everything I'll tell you about is under 100 qubits, and they all involve forces like this.
Excuse me.
Yeah.
The degree of freedom up and down, what is that? Is that actually literally up and down?
No, that's the spin.
The spin, okay.
Yeah. We don't want to use the motion of the ion as a memory. We use it as a bus to allow us to hook together memories. You know, one thing I would point out, contrasting with neutral atoms, is that I didn't really talk much about the confinement of these ions because it's based on the charge of the ions, and it doesn't distort in any way whatsoever the qubit. That's a very important point. We don't have to worry about systematics of confinement of the qubit as disturbing the qubit. That's also why these ions make some of the best atomic clocks out there. Neutral atoms make very good atomic clocks as well, and they benefit by having lots and lots of atoms. But the control of the individual atoms is you know, this is really the most mature system out there. Okay, so if you've ever seen an atomic physics lab, it looks like a mess, and we've spent a good part of the last few years systematizing our small quantum computer, and pretty much everything you're used to seeing in an AMO optical bench is in this meter cube box. And the project in this laboratory is actually funded by IARPA to build a logical qubit. That is to make a particular, I think of error correction as a particular application of a quantum computer. We encode and decode and measure. And the laser, everything that's important is in this box, and it stays closed for months at a time. Everything's automatically controlled outside. And this is not something that you can typically do at a university, so it's not a small budget from IARPA, but we also have folded in performers from external places. Coherent makes that laser I talked about. It has a special modification they've helped us with. Harris makes an optical switch I didn't talk about at all. Cold Quanta helps us with vacuum chambers. AOSense makes CW lasers for laser cooling and detection. And the Sandia makes this chip trap out of silicon. It's plated with gold. There are about 100 electrodes here, and the ions float about 1/10 of a millimeter above that. Okay? So there's a lot of engineering, a lot of classical control. And again, that's really where all the gains will be in coming years in this system. So when we built the precursor to this, it was on a regular optical table. We started with just 5 qubits because one of the electrodes was broken. It wasn't this trap, it was a homemade trap, and we were hoping to trap up to 32. We could only hold 5 to 10. But we had 5, and they were fully connected, very high quality. So we started doing experiments that were way better than what was available on the IBM Quantum Experience, right around the same time. So a lot of the folks that used the IBM system gave us calls. We were not on the cloud, like IBM, and they wanted to run routines. And this is going to school for me. I mean, we ended up learning lots about magnetic spin chains, phase transitions, and lots of things in this field. And I'm not going to talk about nearly any of these, but what's been fun is all the collaborations. People just come out of left field, and it can take up to a year to really get things going. You know, the first phone call is, yeah, we can't do that, thanks. Or, yeah, I don't really understand that, or I don't think it's interesting. But we're, like I said, going to school again and learning different techniques, and we still come back to the potential collaborators and say, no, we can't do that. Can you maybe make it different so that we can do an alternate circuit? And so there's a lot of iteration. It takes months. And then the first generations of experiments don't look great. And it takes a long time. But each of these collaborations, I mean, it's been pretty fun over the last several years. And I think in particular, we've run a few experiments, and we hope to do a lot more that touch this field. And that is using these things to simulate, even at a small scale, dynamics or even equilibrium states that are of interest to cosmology. And the first one, this is from a couple years ago, I don't want to dwell on it too much, is a litmus test for scrambling, which, and again, before I met Benny Yoshida and Norm Yao, I guess I'd heard the term scrambling, but I certainly didn't understand it. I think I visited Stanford a couple years ago as well and learned even a little more about its relevance to black holes and the fate of information when thrown into a black hole. So you've probably seen this, and it's sort of maybe a simpler case of the circuit that I think was quoted from the Google X group and collaborators yesterday. It's basically a teleportation circuit that tests whether a particular unitary scrambles or not. And so once again, lower your sights. This is 7 qubits, and we're testing a 3-qubit unitary only. But 3 is the smallest unitary you need to show the difference between scrambling and entanglement, of course. So the idea is to implement U and its inverse. So the time reversal character is sort of in here. And there are different entanglements that we have to run between these qubit pairs. And yeah, again, I hate to model a black hole as a 3-qubit unitary, but that's the idea here. We're not studying black hole dynamics or anything like that. We're just testing. You can plug any U you want in here, and the question is, does it scramble or not? With 3, maybe there are easy proofs to show that, maybe even with 7 or 8. But this will get hard as U grows, no doubt. And the idea, as you heard yesterday, is that this arbitrary input state, if and only if that unitary scrambles, do you get a good rendition of that initial state at the output. Okay, and what did we use for U? Sort of a generic circuit here. I won't get into the details except to note there is a continuous parameter in here in these rotations, and that allows us to tune this unitary from scrambling and not scrambling. When theta is 0, it does not scramble, and when theta is pi over 2, we expect it to maximally scramble. And so this is the data. Once again, lower your sights. Again, the threshold of 0.5 being interesting. Indeed, as theta went to pi over 2, the teleportation fidelity grew. There are a lot of gates here, by the way. 7 qubits and maybe, I don't know, 60 or so 1 and 2 qubit gates. And these gates are about 1% error stricken, meaning that this expected error, it's not ridiculous, but when we scale this up to bigger sizes, we need better than 99% fidelity. Okay, and you can also see the requirement on full connections here. There's kind of non-local interactions going on that, of course, you're going to need. That's part of the interest in this in scrambling, of course. Now, another state. I was delighted to hear that the thermofield double state is some people's favorite state, and I didn't know what it was until Tim Say pointed this out to us a couple years ago. Tim is somewhere here in the audience. So we basically generated a very small TFD state. Again, 6 qubits, so this is a TFD state with 3 plus 3, really small stuff. Now, the way we generated it was mildly interesting. It was following a derivative of this quantum approximate optimization algorithm, QAOA. And the idea here is to, of these 6 qubits, we first entangle them pairwise to make it basically an infinite temperature TFD state between these 3 and these 3. So it's sort of like having the infinite temperature version, which is sort of a trivial TFD state. And then we apply several layers of gates. Again, I won't go into the details of all these. It's not clear exactly how many layers of these gates you might need to make a TFD state, but it turns out, and Tim has worked on this quite rigorously, that given the number of, I guess for us, n is 3, so we only need roughly n over 2 layers to generate, in principle, the perfect TFD state. So for 3, we only need 1 layer of this. So what we're doing here is we're doing Z rotations, and then we're doing entanglement within one side, and then entanglement along X and Z from A to B. Okay? So we're presumably making this TFD state, and again, if you're interested in more details, you can consult this preprint. I forgot to mention, the TFD state is with respect to a nearest neighbor Ising model with 1 all the way through 6 and the 6 all the way through 1. So it's nearest neighbor in a ring. And we can say.
The qubits divide into a pair of 3
Yeah,
and 3.
yeah, 3 plus 3.
The Hamiltonian should only act on 3 of them.
Let's see now. But let's see. They're.
We're supposed to be talking about entangling 2 things which don't interact with each other.
That's right. So that.
3 and 3.
Right.
So why do we have 6? Why do we have?
Tim, is this sum over all 6 or is it just 3? The Hamiltonian is just the 3. So it's 3. It's separated then. That's right. Yeah. Sorry. Thanks. So it's a tiny ring. Yes. Yeah. That's right.
Good.
With 3. Yeah. All right. Have to lower your sights. Just keep going down. All right. So this is a little hard to describe the data here, but what we have here, let's pay attention to the top, what we expect in theory. Now, there are a lot of circuits in here because we're varying the effective temperature of that Hamiltonian in the state generation. Now, what we're plotting here are the blue lines are the single particle measurements of X, Y, and Z. This first column is X. This is Y and Z. And you can see along the z direction, no matter what temperature you have, there's no projection of the spin along x or y, but then z sort of follows what you'd expect, a Boltzmann distribution given by the temperature. And at high temperature, there's no z value as well. And now we measure correlators between the two systems, between the 3 on the left, 3 on the right, and then the 3 possible correlations within a system. And I won't get into details too much about what you might expect here, but these curves, sort of the bottom row is the experiment compared to the theory. It's okay. Again, we have lots of circuits, lots of gates here, and there are errors. They aren't perfect, but it's sort of consistent with what we would have expected. Again, I'm not sure exactly what to do with this TFT. We would like to scale it up larger, but if there are other measurements that might be of interest here, we're all ears.
You measure the two-sided correlation?
Yeah.
You can measure them as a function of time, too.
Yeah. We can measure n-site correlations. We have single-shot, nearly perfect measurements.
Have you measured the two-sided correlations as a function of time?
Well, that's the green plots here along x, y, and z. Oh, sorry. Not as a function of time. We're just making the state.
Make the state, but then you could.
That Hamiltonian and see how the correlator.
Right.
Yes, I guess that's right.
That's an interesting thing to do.
Okay. At first glance, I'm thinking if each system, you expect the entanglement to grow, I guess. Is that right?
No. The entanglement is frozen in because they're not interacting with each other. But you should find the correlation between the two sides decrease.
Uh-huh.
Because they get scrambled.
Because they get scrambled.
This correlation is simple at t equals 0, but then as you evolve it, the entangled buddies kind of spread out, so you keep looking at the same.
Okay, so we can talk about this later.
Okay, yeah, no, thanks. All right, so yeah, I mean, you can look at that archive as well. We also prepared, using this QAOA method, critical states of the transverse icing model. Okay, so I want to now jump a half a mile away from my lab at the university to IonQ, and I was indeed CEO of the company, kind of not unwillingly, but unwittingly. I had to step in when our first CEO left, so I took a leave from the university for about 9 months. Now I'm happy to say I'm back in my real world of research. But IonQ is clearly it's a company, a startup, it's venture capital funded, they're making systems. Based on the footprint that I showed you from the university, they've made 4 so far, 1, 2, and 3. And what they have that we don't at the university is just excellent electrical engineering, FPGA design, and also software development. 2/3 or 3/4 of the company, they're not quantum trained at all, and that's sort of what we want. These are things that we could never do at university. And at IonQ, they've put a lot of work in the automation of these things. So for instance, in software, we ask for 24 qubits exactly. This is a real-time video. We load them one at a time through a tiny hole from the back of this chip, and then we merge them with the existing crystal that's here. And as soon as the camera recognizes there's 24, they're even zigzag, we stretch them out to make them straight, and then focus the optical objective and ready to go. And so the loading is well under a minute, and the lifetime of these it's a good question. A lifetime can be anywhere from 20 minutes to many hours. Depends on lots of things you don't quite understand. But we know how to make that lifetime a lot longer by going cold. I'll maybe comment on this a little bit. Not dilution refrigerator cold, but just 4 Kelvin. This is a room temperature system. So at IonQ, they've been running circuits, sort of standard circuits, benchmarks, Oracle circuits that are kind of useless. If you look in the textbook, you'll find something like this Bernstein-Vazirani algorithm. There's some hidden information in the circuit structure itself, and if you're given this quantum computer, what is that hidden information? Sort of like the game of 20 questions. And this requires a serious number of gates, and this is BV with 10 plus 1 ancilla, and we're now running it on about 20 qubits these days. So it's a very capable system, and of course we want to do something more interesting, and we have indeed done a warm-up in a variational algorithm that simulates the water molecule. This is a popular algorithm in quantum computing these days, these variational quantum eigensolvers. And in this case, the water molecule has 10 electrons, and when you calculate all the fermionic coupling terms, there's many of them. If you want to get an accurate rendition of the ground state, which we know exactly, water's simple. But when we add more terms to the Hamiltonian and we map them with an appropriate Fermi operator mapping to spins, we end up with circuits that have some number of gates, some number of qubits, and some number of gates. This is all theory right now. I want to point out that we hit diminishing returns right about here. This orange line is KT, so we don't need to really get too far deep into KT. So with 15 terms, we need 10 qubits and about 650 gates. Now, what's important is these are assuming full connectivity gates, but they're also assuming controlled NOT gates and Hadamard gates, the textbook gates. We actually have icing gates with a continuous parameter in the icing evolution. And we compressed it down to about 140 gates with no approximations. And this is an upper level issue. It's not physics anymore. It's more about quantum computer gate compilation and compression. And that's something we can do right now. Now, at IonQ, we haven't marched. This is the energy offset from minus 75 Hartrees. And we haven't run all these terms yet. They take a long time. But in about, I think it's about a solid week of data, we have, there we go. With a solid week of data, we've just done the first 3 terms. And we're kind of happy about this. These are small circuits, but the error bars, statistical and systematic, are of order KT, so that's pretty good. But we hope to soon kind of march down here. And I point this out because I'm now going to plot this on, I'm going to press the y-axis and show the same data here with the same error bars compared to previous work done mostly with superconducting systems that have limited gate depth. Also another ion trap experiment in here. And the point here is that if you're going to do these variational calculations, you need to use the ith value of your iteration as an input to the next one. And you can clearly see why they stopped, because it's diverging from what you expect. So this just goes to show you that these ion trap systems can have pretty deep circuits to do these things.
So the theory was a calculation using a classical computer, quantum computer.
The theory, yes. The theory is all classical simulation. We know it. I mean, we know the answer too, so that always helps. Now, I'm sort of running out of time here, but in terms of quantum simulation, we don't need to focus tweezers on each individual atom. If we have a global interaction that hits all of them, we can realize a fully connected icing model and, interestingly, tune the range of the interaction by simply tuning this laser appropriately. Okay? So we've run a number of experiments in this regime, so-called global type experiments, and these can hit many topics in, for instance, quantum thermodynamics and phase transitions and so forth. As an example of this, with slight modifications, we can get this flip-flop model by adding colors to the laser. I won't, don't have time to talk about that too much, but in this particular experiment, there are 22 spins, and we're hitting them with a global laser beam that gives rise to an all-on-all icing coupling with a fairly long tail. The exponent is smaller than the dimension of the system spatially, so this is really not one, you shouldn't think 1D here anymore. Now, at time equals 0, we prepared this highly non-equilibrium state, one excitation up, all down. And of course, this Hamiltonian preserves the number of excitations. So after a long time, long meaning 36 over J, you might not say that's too long, but this is a fully connected, J is nearest neighbor J, and this is a fully connected system. So the excitation did, in fact, you can see that it made the whole trip, but the center of the excitation barely moved. The dynamics are really slow here, even though JT was 36. And so, if you add up the brightness of this image, which is obviously averaged over many runs, you get exactly one excitation. And this is basically a very clean example of what's called PreThermal Dynamics. And if we look at the center of excitation, where -1 is to the left, +1 is to the right, we expect the thermal value to be 0 by symmetry. And forget the smooth curve here, the brown one, but the raw data in blue here shows the center of excitation sort of saturates. Now, we would love to go to JT of 36 million and then see it thermalize. But even though our qubits are perfect, the laser has noise on it, classical noise. And that basically adds noise to this. It's effectively like having decoherence, even though it's induced. So we can't run that far. Now, the way I naively think of prethermal time behavior is that there's a small gap in the system, and it just takes a long time for that gap to be noticed. That's one way to look at it. So the prethermal time scale is the average gap, which is pretty fast, and then this tiny gap in these highly frustrated systems will give this prethermal behavior. Now, we expect at a long time this blue line should come up to 0. And we've used this to do further experiments to see phenomena that are consistent with many body localization, even in a small system, and also time crystals. I don't have time to talk about that. I wanted to briefly mention our simulation with the biggest number of spins. It's slightly over 50. The number 53 keeps coming up. And we actually had, this was 2 years ago. We got there first, 53. Here we're doing a quench experiment. And this is sometimes called a dynamical phase transition, which doesn't make a whole lot of sense. Phases usually imply some equilibrium process. But here we have our friend, the transverse icing model with long range. And there's a competition between the order along x, given by this long range form, and the exponent's about 1 in this case, and an applied B field. We prepare long x, and then we measure long x. Actually, a pretty simple experiment. Well, if we measure the magnetization, which is our case, just the brightness of the chain, we see that when B over J is a bit less than 1, we do see, indeed, a little bit of wiggles from the field, but not too much here because we're already prepared along x. We don't expect much evolution. But when B over J is bigger, we see a totally different type of evolution. Now, I wouldn't call this a phase transition. You might call it a crossover or something, but it's just complex dynamics either way. If we measure correlators, these are two-body correlators, all n squared of them, averaged, this time versus the number of spins in the system. Here we're plotting versus B over J. We sort of see a minimum here. The dotted lines are mean field, so you can see that mean field doesn't really work very well over certain regimes. And as the number of spins grows, we see this dip gets a little bit sharper. When you go to infinity, we have an analytic solution. It should be a logarithmic divergence, but we were a little disappointed that that wasn't very pointy. So we measured an n-body correlator. And this is a very weird order parameter. It's the mean domain, the largest domain size in the system. We average that over many runs. And this time, when we plot the mean of the largest domain size in the system versus B over J, we do see a much sharper kink. Much like what Misha showed in the neutral line system, we couldn't calculate this before. Not that you'd want to calculate it. It's a long-range, weird interacting system. But once again, this is a simulator, not really a computer. But it does allow us to measure things that we might not have been able to get before. Now, how are we going to scale the system? I mentioned when we go cold, the chain lifetimes are much longer. And this picture is eventually will be an example of about well over 100 qubits, and they stay there all day. This defect, it's a 172 isotope of ytterbium, and it stayed in the same position all day as long as the power was on. So it's not about going cold, it's about lowering the pressure, getting rid of these collisions. Now, in the long run, we know we can scale with a few technologies. They're hard technologies, but they're not quantum. This is all about classical control. In this case, we could imagine having sort of a tape and a head system. The head are laser beams that allow us to have connectivity over however many laser beams we have. And the tape is moving a bunch of ions through that tape. And again, the ion lifetime can be very long. So this should be possible. With Dave Lyland, we've thought for a long time about how to shuttle around corners and make more complicated chip traps to scale up. And then beyond that, I think we can go optical and have modules, very much like a multi-core classical system. We have modules of maybe 50 qubits and then have single photons connect these atoms from point to point. I haven't showed you the background of that, but all of the technology behind that has been demonstrated at small levels, and it's just a question of systems engineering to scale. We might want to use some of the neat integrated photonic circuits people are building these days. So this is my last slide. You've seen it before. I borrowed it from Hartmut Neven, and putting current and projected to the next few year ion trap experiments, we are poised to be doing things that are beyond this red line, so-called supremacy line. Doesn't mean they're interesting. So I think in a sense we have to build these machines and see what's interesting and go back and forth. I think back at the university side, I'm more excited because I think the physics interest will be much better than any potential corporate user in the next 3 to 5 years or so. And we would love to be able to adapt our system to physics problems that are of interest. Thank you. That's all I have.